Hello, my dear students. Welcome you all to Sri Jayendra Rank Zone classes. I am your mentor and your friend for the subject chemistry, and I will be taking the organic chemistry. My dear students, in the last lecture, we started to discuss some common polymers. We started our journey with the natural rubber. We discussed natural rubber, that is polyisoprene. We discussed about vulcanization of rubber. Today I'm going to start with the synthetic rubber, but before starting with synthetic rubber, I would like to tell some more points regarding vulcanized rubber and the types of copolymers. So, vulcanized rubber, it depends upon the percentage incorporation of sulfur added. The strength of vulcanized rubber can be determined. For example, 5% of sulfur added is used to make tires, and 30% of sulfur is added to make battery case rubber. As you know, vulcanized rubber is wear and tear resistant. Vulcanized rubber wear and tear resistant, and it is almost insoluble in all common solvents. So these points will help to differentiate between natural rubber and the vulcanized rubber. Now, types of copolymer. Depending upon the type of monomeric units used for the polymerization process, the polymers are classified into homopolymers and copolymers as we have discussed in the previous lecture. Okay, so copolymers, they are further copolymerization can be further discussed as that copolymerization, it is the mixture of or it is a combination of different monomeric units structurally and functionally. Okay, so copolymerization helps to make polymers having different properties. Okay, the first category of copolymer is alternating copolymer, copolymer in which monomeric units they are alternatively placed like AB pattern, like this. Okay. Random copolymer. Random copolymerization, it involves the introduction of monomeric units to be placed, or these monomeric units they combine or they occupy any position, any random position. So it is the distribution of monomers in random fashion, random fashion, like AA, BA, like this. Okay. Then comes the block copolymers, in which there are blocks of each monomeric unit. Alternating with each other, alternating with each other. Okay, like here you can see that block of 4, a block of 3. So this is block copolymer. Then comes the graft copolymer. It contains branches derived from one monomer, which is grafted onto the backbone of polymerization, backbone derived from another monomer. When we are going to add the branches of one monomeric unit on the polymeric backbone of the other monomeric unit. Like for example, we are having a backbone of A, like this. This is homopolymerization. Then we introduce a branching of B, 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 like this. So this is graft copolymer. Okay. Now, after this, we are going to discuss the synthetic rubbers. Synthetic rubber. Now, the first category of synthetic rubber we are going to talk about is Bunas. Okay, Bunas is also known as styrene butadiene copolymer, butadiene copolymer or SBR. Okay, the monomeric units are 1,4 butadiene, 75%, and styrene, 25%, which makes a polymeric chain like this. Okay, whole N. This is the formula of SBR or butadiene styrene copolymer. Okay, the applications are making of tire, and other mechanical rubber goods. And other mechanical rubber goods. Okay, then comes neoprene, which is basically 2-chloroprene, CH2 double bond C. Okay, now the polymeric formula is it is used in making of automobiles, refrigerator parts, and electric wire. This is neoprene, which is a polymer of 2-chloro 1,4 butadiene. Okay, used in making of automobiles, refrigerator parts, and electric wire. Next comes the butyl rubber, which is a polymer of the monomeric units are isobutylene, 98%, plus isoprene, that is 2-methyl 1,4 butadiene, 2 to 3%. Okay, this is isobutylene, 98%, plus isoprene, that is 2-methyl 1,4 butadiene. Okay, these are the monomeric units. Applications: making of tire, toys, tubes, etc. This is butyl rubber. Now comes Buna-S or nitrile rubber. The monomeric units are butadiene, 75%, acrylonitrile, 25%. Okay, the polymer obtained is it is used for making of fuel tanks. In making of fuel tanks, Buna-N. Okay. Next is polysulfide rubber or thiocol. The monomeric units are ethylene dichloride. This is vicinal chloride. Plus sodium tetrasulfide. Okay. It is used in the manufacturing of hoses, tank linings, engine gasket, and rocket fuel. Okay. Next is silicon rubber. This is chlorosilanes, which is the monomer. Okay, used to make silicon rubber. Okay, now polyurethane rubber. The monomers are ethylene glycol, plus ethylene isocyanate. It is used in the manufacturing of fiber, paints, think of fibers, paints, and heat insulator. Okay, bunion, which is nitrile rubber, it is resistant against the action of petrol. Petrol and oils. That is why it is used to make oil seal kits. Okay, it is also used to make hoses, tank linings. Okay, same uses. Understood? Neoprene, I have told you. Yeah. Now comes their question is in case of BUNA-S or SBR, BU stands for butadiene, Na stands for sodium, and S stands for styrene. In case of BUNA-N, everything remains same. Just N stands for acrylonitrile. Okay. Now we will be discussing about the low density polythene and high density polythene as we have already discussed in the classification part. Okay. But LDPE, sorry, low density polythene and high density polythene, they are very important polymers which are used nowadays. Okay. So these are the addition polymers. Rubbers we have discussed all types of rubbers, natural, synthetic, polythene or polyethylene. There are two types, low density polythene and high density polythene. Okay. Low density polythene or LDP. It is manufactured by heating ethylene at a temperature of 350 to 570 Kelvin, pressure 1000 to 2000 atmospheres in the presence of traces of oxygen which will generate the free radicals. Okay. Or peroxide initiators. Homopolymerization. Polyethylene. Okay. It is obtained by free radical polymerization. Okay. So free radical polymerization, that is addition polymerization. Okay. And hydrogen atom abstraction. Hydrogen abstraction. Okay. It is highly branched, loose packaging, less density or low density, and low melting point. Low melting point, 384 Kelvin. Okay, that is why it is known as what? Low density polythene. Okay, it is of moderate tensile strength and transparent. It is chemically inert. These are the properties. Now, the uses. Low density polythene is used as a packaging material, insulating material, flexible pipes to make flexible pipes, toys, and squeeze bottles. Okay. Next is the high density polythene or HDP. High density polythene or HDP. It is prepared by heating ethene in a hydrocarbon solvent at about 333 to 343 Kelvin temperature. Pressure is less, low pressure, 6 to 7 atm. In the presence of Ziegler-Natta catalyst, Ziegler-Natta catalyst is basically it is a mixture of triethyl aluminum plus titanium tetrachloride, TiCl. Okay, it is straight chain, not no branches, linear chain, show high levels of packaging, close packaging, high density, high melting point, It is harder, tougher, and of greater tensile strength. Understood? Okay. Uses helps to make containers, manufacturing or making of containers like buckets, dustbins, and rigid pipes, houseware pipes. Okay. Now, next is PTFE, polytetrafluoroethylene. Okay, or Teflon, also known as Teflon. It is an addition polymer. The monomer involved is tetrafluoroethane. Okay, the reaction is carried out in presence of persulfate catalyst. Okay, like ammonium persulfate. This is Teflon. This is tetrafluoroethane. It is chemically inert. Tough material. Resistant against heat and attack of corrosive agents like acids, bases. Okay, and it is a conductor of electricity. Uses to make heat resistant materials for coating articles and cookwares to make them non-sticky panwares, for making gaskets, pump packings, valves, oil seals, etc. This is PTFE, polytetrafluoroethylene, which is a polymer of tetrafluoroethane. Okay. Then comes polymonochlorotrifluoroethylene, polymonochlorotrifluoroethylene, also known as PCTFE. The monomeric unit is ClFC double bond CF2. Monofluoro. Okay. Undergoes homopolymerization. Okay. The properties are: it is less resistant to heat and chemical attacks. Due to presence of chlorine atoms. Then polyacrylonitriles or PAN. Okay. It is a polymerized product of vinyl cyanide. The monomer is vinyl cyanide or acrylonitrile. Okay. It undergoes addition polymerization. Okay. Also known as orolone. Presence of peroxide catalyst. Also known as orolone or acrylane. Okay. Vinyl cyanide can be prepared by the help of ethylene attack with HCN in the presence of BaCN whole twice, or CuCl in the presence of HCl to form vinyl cyanide. Okay. The catalyst used, such as molybdenum oxide, MO2O3, CO2O3, and Al2O3 at 723 Kelvin to convert propene in the presence of air and ammonia to form vinyl cyanide. Understood? So all these are addition polymers we discussed. Okay. Uses. It is used as an artificial wool for making blankets, sweaters, bathing suits, etc. It is also used to make synthetic carpets. Properties. It is hard, horny, and high melting substance. Understood? Now comes we discuss all types of addition polymers. Now condensation polymers, in which condensation reaction is carried out. Okay. As you know, condensation reaction, it follows step growth polymerization. The first example is polyester. They are the products of dicarboxylic acid and diols. Okay, they have ester linkages. That is why the name is given polyester. Okay, example is sterylene, which is a polymer of ethylene glycol plus terphthalic acid. Okay, These are the monomers of pterylene. The reaction is carried out, the reaction conditions carried out at a temperature of 420 to 460 Kelvin. Catalyst zinc acetate and antimony trioxide. Okay, also known as Dacron. Okay, ethylene glycol, ethane 1,2 diol plus terphthalic acid, acid and alcohol, they form ester linkage. Catalyst is here. Okay, it has a very strong fiber. It is grease resistant, durable, and has low moisture content. It is used in blending with cotton, to form terracotta, blended with wool. Okay, it is used as glass reinforcing material in safety helmets. And it is also used to make recording tapes. Also used to make recording tapes. This is about pterylene. Okay. Now comes glyptal. It is also a polymer of ethylene glycol plus phthalic acid. benzene 1,2 dicarboxylic acid. Okay, it is a cross-linked polymer, network cross-linked polymer, cross-linked polymer, right? It is used to make paint, for making building materials, such as asbestos cement. Okay. Next is polyamides. They have amide linkages. Okay. And they are commonly known as nylons. First is nylon 66. The monomeric units are hexamethylene diamine, and the second monomeric unit is adipic acid. These are the monomers, right? You can see hexamethylene diamine is having 6 carbon, and adipic acid is also having 6 carbon. Hydration. Okay. This is nylon 66. Okay. It is used to make bristles of brushes, in textile industries, okay, to make sheets. It is also blended with wool to make socks and sweaters. Used to make climbing ropes and cords. So this is the first compound of polyamide, that is nylon 66. Next come nylon 6. which includes only one monomer, caprolactam. Okay, caprolactam is obtained from cyclohexane hydroxylamine to form a addition product, oxime, reacts with H2SO4, caprolactam, when heated in the presence of traces of water, forms aminocaproic acid. Aminocaproic acid. Okay. Aminocaproic acid is this is aminocaproic acid, which is 6-aminohexanoic acid actually. It is heated, water is lost, from condensation polymer. From condensation polymer. Condensation polymer. Okay. It is used to make tire cords, fabrics, and ropes. So my dear students, we have discussed polyamides and now we are left with formaldehyde resins, which include formaldehyde melamine resin and formaldehyde phenol resin. That is bakelite. Okay. So I will be meeting in the next turn. We will discuss the leftover part, which includes the molecular masses of polymers, formaldehyde resins, and the biodegradable polymers. Till then, bye bye. Take care. Stay safe. Stay healthy.